In this video, we're going to revisit the very foundations of the ABR technique, the essence of ABR technique, compression without distortion. So that's a kind of compact formula that could be used to describe it, and it's important in the context of understanding of why ABR technique is special and how compressional ABR technique is different from hundreds of compressional methods that existed for centuries. The essence of the ABR technique is both straightforward and counterintuitive at the same time. So compression without distortion. What does it mean? So distortion would actually refer to the elastic deformation of the outer walls of the body. So we are looking for the compression without elastic deformation of the outer walls, such as the combined muscular coat and combined skeletal shell. How is it possible? It's possible in the case when the compression only travels within the biointegral range of response. The biointegral range of response. Why is it so important? I'm going to give an integrated overview and then going to zoom into the details afterwards. So the biointegral range of response gives us the uniform converging compression from the outside that translates into the uniform diverging response at the target fascia layers, inducing the remodeling in the weak elements via mechanical transduction. And that's different from the non-uniform conventional elastic deformation or distortion, which actually only maintains the status quo because of the preservation of existent imbalances, where the weak tissue elements remain weak and the strong elements keep getting stronger. So when we talk about the essence of ABR, we have to cover two components: the volumetric perspective and the layered perspective, because obviously when we look at the cross section of the body, and again I'm going to return to this over and over again, that no matter how complex is the shape of the body externally, internally we still follow the original radial body plan. So volumetric perspective is the one that covers or addresses or appeals to this completed volume if we take any cross section. So the volumetric perspective of the ABR in that sense would be the response to external compression in the context of the fundamental radial organization of a human body. It's also called radial symmetry, but radial organization is an umbrella word that explains the overall body plan. So with the volumetric perspective, we are going to look at the response to compression from the outside, the way that it translates into the counter action from within. And in the layered perspective, we take a different facet or a different angle, to say so, and we look at it from what I call a sponge kick. Obviously that's just a metaphor, but that helps you to understand the principle, because everything is arranged in layers, and from the layered perspective we consider it outside of the volumetric context, outside of the shape. We just look at the sequential positioning or sequential arrangement of the layers and how we can actually get to the internal weaker layers by getting through or bypassing the strong outer layers, which are producing this stress shielding effect. Means that they absorb all the impacts normally, all the deformation impacts that come at the body. So they, in that sense, if we continue the sponge cake analogy, work as this kind of outer glazing. whilst we actually want to address the weaker, deeper levels. So this is the rough schematics that we are going to use for that purpose, where this is the source of application, this is the target layer, and these arrows would indicate the response of the target layer. So let's dig deeper and proceed to the volumetric perspective, where we're looking at the compression without distortion. The key word that I have already used was the biotensegrel response. So a biotensegrel response indicates uniform compression without distortion. So in that sense, these two, they work together. Compression without distortion equals biotensegrel response, and it equals uniformity, unlike the presence of distortion. So in that sense, I'm using the term distortion as opposed to deformation, so that the certain deformation as the change of shape is as a kind of as loading is being present, but it happens without distortion. So, and what is the key for the biotensegrel response? That no matter what direction an impact comes from, it translates into the uniform response that happens within the entire volume. And from that perspective, it doesn't matter how many impact points are there, whether it's a single impact point, whether it's a single impact point that comes at an angle, whether there are multiple impact points, it doesn't matter. The product is always the same, unified, volumetric, uniform response. And with this, we come to this central point. Biotensegrel compressional loading, the blue arrows in that sense, lead to biotensegrel counter response from within the body. So that's the unique property of the biotensegrel range. In that sense, we're getting back to the physics fundamentals, action, counter action. So if we deliver the external loading, the response is the counter action. So that brings us back to the essence of the laws of physics. So, and the unique property of the biotensegrel range is that the compression from the outside, no matter where it comes from, I already said that, translates and converts into uniform expanding counteraction. So compression reflects into the expansion. The one that converges, a response goes into the diverging pattern. So as if we were pressing simultaneously from everywhere and generating the proportional response from within. So that's, as I said, the key. If our compression, when we do some technical applications, if our compression stays within this biotensegrel range, or the without distortion range, right? Then and only then we get the uniform biotensegrel counter response from the body. And this biotensegrel compressional range, if we deliver it, gives us this uniform expanding counteraction. And what is most important about it? The opportunity to correct the existent imbalances. Because at the end of the day, all the troubles that you face with the cerebral palsy kids, or in any sort of pronounced musculoskeletal challenges and deformities, we get back to the essence. And the essence is the imbalance. There are elements that are excessively strong and there are elements that are excessively weak. And the thing is that everyone tends to try to fight with the excessively strong elements without having much of the effective tools of addressing the elements that are weak. And this is the key, that uniform loading within the biotensegrel loading pattern, or biotensegrel compression, gives us uniform counter response that allows to engage the weakest elements within the imbalance profile. That's the key. And the problem of the loading with distortion is the presence of the stress shielding effect, where the strong elements take the lion's share of the external mechanical load, and therefore the weakest, they are being away from action. They are not addressed. And here it's the other way around. With the bite-integral counter response, it's the weakest elements, because it's uniform, right? So the weakest elements, which are the hungriest for external mechanical feeding, if I might use this analogy. So that's the key. That's the key solution for the problem of the fundamental imbalance. So let's continue to illustrate these points a little bit further, because they are really, really important. So this is the regular response. Compression causes distortion. What happens, you see, if the loading comes, for instance, from this top to bottom direction, the object of impact, in that sense, well, would be signifying, or the image of the cross-section of the body, it gets narrower, decreases, the height decreases in the direction of loading, and there is the bulge that takes place in the other directions. So if the direction of loading changes, so does the response. So if I'm now delivering the compression from across, now we're having the bulge that comes along. So this is, if this was a left to right loading, then top, bottom, or front, back actually respond with bulging. So this is the response which is typical, regular, say normal, the one which is being experienced, that you'll try with any kind of inanimate objects, and that's what you're going to get most of the time. Try to squeeze the ball, try to squeeze anything. You're going to have this. There is a compression, there is a distortion, which comes as the reduction of height in the direction of the depression, and there is a bulge, because the volume in that sense remains constant, so it redistributes and bulges outwards. So, and once again I want to return to the difference with the bite-integral range, where no matter where you load it from or how many points you use, everything comes uniformly. That's the key. That's what makes the bite-integral response so special, so different from the regular responses that you normally experience in everyday life, and actually the ones that most, or like all of the regular existent compressional techniques are based on. And that's the key problem. So when there is this factor of distortion, namely the decrease in the direction of compression and bulge in all the other direction, it's irregular, it's non-uniform. And therefore, once it's non-uniform, it translates into this just non-uniform primary elastic counter reaction of the muscular coat and the skeletal shell. And as a result, with this non-uniform response, the imbalance remains. So the status quo of the existent imbalances remains, and actually most of the time it even aggravates. So if we get back to the description of the bite-integral uniform response, what are the key features there? Because it's this unique bite-integral uniform response that we want, very specific. Not just any loading, right? Very specific bite-integral uniform response, because that's the key for addressing the deep imbalances that your child with cerebral palsy in particular would be suffering of. So the key point here, that the response and the loading is volumetric, so independent from the direction of loading, but very sensitive to the profile of loading. So that's the key, right? So it's not about the direction, it's about how you do it. It's about the profile of loading, the sequence, the distribution of sort of the pattern of loading and so on. So that's the key. The second part, which is very important, right? So that this bite-integral uniform response exists in a very limited range. It's not just anywhere, right? It's very limited range. You really have to catch and nurture it, and it's very limited. So it's not accidentally available, to say so. So, and in that sense, this limited range is characterized by two specific properties: the distance of compression and by the profile of loading. Well, profile of loading would describe everything dealing with the way that the forces are being accumulated and the velocity and so on. So that's the essential message which one has to understand about the bite-integral uniform loading and response. It needs to be specifically targeted. It cannot be achieved accidentally just by any sort of response. Plus, there is another thing. It needs or it benefits from the presence of the amplifiers, because that allows us to deal with the sort of matching profile of loading and helps us to get more accurate or somewhat expanded range of the force transfer mediums and expanded range of the availability of the bite-integral response. So that's why the usage of the force transfer mediums is important, and they would vary depending on the external shape or the internal composition of the structure, the target, or of the volume that we target. And here comes a very important caveat, in the sense that some people might say, okay, well, I see this is uniform and this is non-uniform and it's not good. But you see here in this direction, we can sort of, when it loads like that, that's one height and that's another height, right? Why don't we just push one against another and kind of compensate it by loading everything from the outside? Well, that's exactly the flawed thinking that I was trying to point out and demonstrate on this particular graph. So where the blue arrows, right, they would correspond to the loading that comes from the top. So therefore the bulge comes sideways and the compression comes from top to bottom. And the black one corresponds to the loading from the left, so across. So in that sense, the bulge comes top to bottom. But it's important to understand two things. First, no matter how many of those things you put around, it's still going to be dealing with the irregularity of the internal structure. So that means that your elements and pieces are still going to be too large, right? So the platforms of application. So you're going to cause this local bulges and the depression. So in that sense, it's you zoom, try to make smaller patches that you deliver the applications through, but nonetheless, it's still not going to change the quality of the response. Because again, the key here is that the response is internal and we are dealing with the multi-layered structure. The body is multi-layered. So therefore, no matter what you put on the outside, it's the internal response that matters. So therefore, actually, even when you try to compensate by loading evenly, even though it's impractical, with all sorts of directions, actually your end result is going to be a double distortion instead of the intended correction. So that's a very important warning that I'd like to point out here, because typically say the orthopedic thinking. It's very much goes along these lines, trying to force a certain body element into a sort of artificial position, expecting that it's going to kind of somehow mold into this shape. So that's obviously an outdated illusion. So this way we're able to formulate the key thing that we need if we want to correct the imbalances. We have to learn, we have to organize our technique, our impact, our external compression in such a way that it will follow the biointegral counter response, right? That it will generate, it will induce. And for this, we need to come up with the external loading that would follow the biointegral properties. So that's the essence of what we are looking for. So again, I want you to point out, I want you to understand that ABR is a technique in that sense which shaped by design, shaped for a purpose. It's not accidental finding or accidental application, just press, push harder. It's a very specific, deliberate, targeted and application made by design. So this is the key. If our compression stays within the biointegral range, within the range of compression without distortion, then and only then we are going to get the biointegral volumetric counter response from the body. So where the compression from the outside, even local one, converts into the expanding volumetric counteraction from inside. And this magic only occurs, only happens within the biointegral range. That's the key. And within the biointegral range, locally applied compression converts into volumetric expanding counteraction, as if we were truly compressing simultaneously from everywhere, right? But we don't do it by trying it primitively, by just pushing everywhere. We do it from within. That's the key. And that's a number of key messages that we need to understand about the technical ways of doing things. So total volumetric impact, it's not about surrounding the body over the entire circumference with endless number of local patches. It's about getting the biointegral modality of compression. Compression without distortion. So all we need is just to have a large enough sector. Of course, we can't get the biointegral range of response with the tiny piece like this. That wouldn't work. So that's what I'm saying. It's by design. It's not that little, but you don't need that much. So you need just enough, and you need to generate this particular type of response. So if we summarize it, that means that correct mode of compression, correct mode of loading that fits the biointegral definition, that is compatible with the biointegral loading profile, is way more important than the size of the contact area. In other words, it's not that you just cover it with patches and do like anything you like. You have to know what you're doing, and you have to be looking for that response. So why is it so important? Because this way we're coming to another key word that I want you to understand and remember and kind of really plant it in your mind. This word sounds complex, but it's not that difficult to understand. Mechanotransduction. Mechano, right, as for mechanical, transduction is being passed on. So it's very intuitive in that sense. So mechanical transduction is a conversion of the external mechanical inputs into the construction of the elementary biological structures via a complex chain of events that eventually reaches the cellular level and the level of the extracellular matrix components, where the fascia is actually laid out and built, right? So the collagen fiber and so on and so on. So for practical uses, you can think of mechanotransduction as some sort of mechanical feeding of tissues, where large external mechanical impacts of the macro level, macro, right, food, being mechanical food, right, are being converted into small enough energy chunks digestible at the micro level, where the actual tissue remodeling, repair, and build takes place. And the usefulness of mechanotransduction for the target biological tissues, namely for the weak fascia structures in your child's body, depends on the geometry of applications, on this profile of loading. The proper name for this is the triaxial stress ellipsoid, where stress is force per area, but I'm not going to load you with this. You just need to understand it has to be the biointegral range. So in that sense, awareness of your actions and proper targeting define the make or break outcome, whether you bring good or whether you're doing something wrong and actually add damage, right? So, and the key challenge with mechanotransduction is the stress shielding. When the stronger elements, namely the outer layers, shield the deeper layers, right? So when you try to deliver compression from the outside, they are the ones, they're the first to report, they're the first to respond. So, and that creates the aggravation of the imbalance. The more you load them, the more they respond in the elastic manner, which is their modality of the development. Boom, what happens? They get stronger and the weak ones remain weaker. So bypassing, overcoming the stress shielding is the key thing. So in essence, we want to avoid this situation. We don't want these stronger elements, fibers, outer layers and so on, absorb this lion's share of the mechanical feeding, right? So we want the ways to get around it, to get the uniform loading. That's the key. So we want to bypass it. But this is not an easy task. And in that sense, the biointegral approach of uniform loading is counterintuitive, because the intuitive thing is when you see the imbalance, you try to chase individual elements, sort of trying to think, well, let's make this excessively strong or slightly weaker, right? And this way the imbalance is going to reduce. This is a dead end. What you need to create a situation of true balance, true uniform loading, and then you're going to get this magical thing happening, that the weakest elements in this sense, they are the ones which are the hungriest, and they would benefit the most because their proportional deficit is the greatest. So that's the key. It's not chasing individual strong elements and trying to kick them down. It's about getting the uniform loading, and that in turn is going to bring the maximum sort of disproportional but positively disproportional share of development via the mechanotransduction for the weakest elements. And the fact is, ABR is the only method that respects the biointegral range. To be precise, we actually the only method which actually brings this point out, because all the other compressional methods just simply mindless, just press and push and try to squeeze something out of the body elastically, not going too far beyond the idea of the toothpaste tube. Well, that's exactly the reason why our results are superior to all the compressional methods. So it's not the compressional method, the compression itself, it's how you make it and what criteria do you satisfy. So, and this brings us to the ABR technique formula. And once you understand the prerequisites, the fundamental path to what we want to achieve, I guess the rest is going to come out naturally and quite straightforward. So, because we effectively and intentionally ask the question, compression without distortion, how is it achieved? And the answer is simple. Via, well, simple but counterintuitive, right? So via the 3Q methodology, the triple Q methodology of ABR. So it's quasi-isotropic, quasi-static, quasi-spherical. Plus we add the use of the force transfer mediums with the specific range of parameters that match the weakest layer that is being targeted. So what are the three Qs, right? First Q is quasi-static, the second Q is quasi-spherical, and the third Q is quasi-isotropic. Well, these are some heavily sounding words, but no worries. In fact, everything is quite simple. So quasi-spherical means that since we intend to address a large volume, we need to maintain a sufficient area of surface coverage throughout the entire duration of application, so that we are going to avoid local sinking and depression into a force transfer medium. So, and as I already mentioned, fortunately for the bite-integral range, in order to address a total volume of sort of compartment of the human body, we don't need a complete sort of surface turn wrap around. There's no necessity. We just need to get sufficient enough sector. And in other words, that quasi-spherical principle simply points out that we are obliged to have a certain minimal area of contact, sufficient for getting a volumetric response, right? And that's the key word, volumetric response. And if this description is not entirely clear, I'm sure it will become obvious once we go further to the next set of pictures. So, but meanwhile, next word here, the first Q was quasi-static, right? Again, very simple. It's super slow, which is again understandable. If you want to be adjusting to this uniform compressional performance, if you want to produce the uniform compressional load, you can't be quick. You can't be sort of delivering excessive acceleration. You have to be uniform in that sense in your movement as well. So that's what is achieved via quasi-static. So again, that's another facet of it, is that the quasi-static also helps us to deliver the maximum to the deeper structures. And the quasi-isotropic actually, to a certain extent, a summarizing word here, right? So means that we don't want to deform any of the surfaces, which is also simple, quite straightforward, right? If we want the uniform response inside, well, the moment we distort any outer surface, we're not going to get anything, right? Because that's going to like transform the lens. Our lens will become bent, twisted, and poorly shaped. So, and for that purpose, we don't want to distort neither a force transfer medium layer nor an outer shell layer, nothing, right? So we want to get compression without distortion. That's the word, right? So that's a summarizing thing for the quasi-isotropic. And that brings us back to the question that we're always being bugged with, right? What's happening? Why there is no visible movement when ABR is being done? Is this, in other words, people are asking, right, because it's so counterintuitive, compression without distortion, is it possible? And another way to phrase it is that compression without distortion, is it practical? Is it going to bring anything? Well, now, once you know about the bite-integral range, you're already more equipped to it, but we have actually numerical proof for this as well. You can find those slides in the other ABR presentations, but here I'm just going to go quickly through it and maybe bring it in a little bit different light. So again, this is one of our key slides, right? Key kind of messages that we want to deliver. That the dramatic difference between the local loading, means the loading with distortion or compression with distortion, and the compression without distortion. So when the question is being asked, compression without distortion, is this possible? Or is this practical? Is anything going to come out of it, like mechanically sort of tangible and palpable? Well, the answer is yes, very much so. And this is the model which is done with the sort of advanced engineering software, which clearly indicates that no matter what force, no matter what magnitude of the force is being used, it's the profile of loading which is the key. If the profile of loading is correct, then, as the slide on the left shows, that the transfer efficiency of the external force internally is more than 600 times greater when you deliver it without distortion than if you were delivering it with. So that's amazing figure, isn't it? And this is the key point, that compression without distortion is not only possible. In that sense, you can see that it has a double benefit. So on the one hand, compression without distortion is perfectly safe because you don't create any local damage potential areas. On the other hand, you get the dramatic 600 times increase of the conversion ratio of what you deliver from the outside, the way that it comes into the inside, right? And that kind of plays into a good loop with the safety, right? Because if you have a great conversion ratio, if you have this effective transmission or transfer, transduction that goes inside, well, you don't need any major forces on the outside. So once you deliver the proper profile of loading, you get your result. But as they say in the infomercials, wait, there is more. And there is more brings us back to our challenge, or like fundamental challenge that I described a bit earlier, that we deal with the real bodies, namely the relationship between the external musculoskeletal coat, or between muscular coat and the muscular and the skeletal shell, and the deep fascial radial core that we actually want to address. Or in other words, is these schematics, right? So where the outer shell, this hard, dense shell, kind of shields the softer, weaker structures that we want to address. So the key point for us is that, well, compression without distortion, is it capable to get its way through this shell? And the answer is yes. That's what we use the force transfer medium for. So force transfer medium, and again, this model is a little bit complex at first glance, but actually it's very straightforward. So what we are having here, we're having on the left and on the right two different profiles of loading and two different effects. So the layer number 4, the lowest, the deepest layer, right, is our target weak tissue. In our sense, say the fascia, but it doesn't matter because it's the general model. So what we want to address is to deliver maximal mechanical input to this structure while respecting this compression without distortion principle. Now, the level number 2 is the outer structure, the shell. That's the shell that shields the internal layers. The shell that on the one hand kind of protects it, right? Because these are the dense outer structure. Protects it from what? Protects it from irregular responses, from regular loading, not from biot-integral loading, from regular loading with distortions and deformations. That's why the shell is strong. But what happens whenever we try to load this shell in the wrong way, well, actually the shell only strengthens. It kind of perceives it as, oh, wow, there are so many challenges, I have to work harder. So what happens? The contrast between the dense and strong outer layer and the weak outer layers is actually only increasing. So if our goal is to bypass the shell and reach the real deep core, that's when we're facing the technical challenge. And that's the challenge that is being solved, and the way that is being solved is described via this model. So I've kind of went on a tangent, but let's get back to it. So number 4 was the target, the weak tissue. That was the shell, the outer structure. Next level is the transfer medium, that's number 2. And number 1 here is the source of force input with the manual application, that would be the hand. So, and this is the matching stiffness. Again, the word stiffness characterizes density, right? Again, that's where the scientific words mismatch with the common usage. So, in that respect, the absolutely amazing effect happens. If this is the weaker structure and this is a dense shell, surprisingly, amazingly, the moment we find the force transfer medium that is matching in stiffness or being actually much softer than the outer shell and being close in its properties, compressional properties, to the deeper target layer, what happens? The magnitude of a transfer increases dramatically, because in this particular picture, sort of the darker the blue, the greater the impact. So that's the absolutely amazing result, where we have this thing that the minimal impact happens in the case when there is the harder outer shell, where there is a mismatch between the outer force transfer medium and the weak target tissue, and on opposite we get the maximum response when we get the soft layers in between. So soft force transfer medium solves this fundamental problem of how to reach the deep layers in the format of compression without distortion. So when we ask the question, is compression without distortion possible? Is anything going to pass through? Yes, very much so. It's going to be a maximum, the impact, again, the conversion of the, no matter what is the outer force, right? The conversion is going to get better if we use the proper force transfer mediums, the soft one, which is matching our weak, deficient target layers. And you can see that by taking this avenue, we actually solved another question, right? Because we started with a description of the volumetric perspective, but then this way we easily build the bridge to the next point, to the layered perspective. Because this particular schematics, this particular profile of loading, and the demonstration that it is possible to target the deeper layer if the force transfer medium is chosen correctly and if the outer loading is done properly, well, that pretty much addresses the sponge key perspective, where we discuss the mismatch between the strong outer layers and the glazing and the weaker sort of spongy, mushy layers that we want to address and where we want to get the response from. So the conclusion and the answer to this big question, is compression without distortion technically possible? Is it practically realistic, or is it valuable? It's very obvious. We can have a strengthening internal impact without external deformation, or without distortion to be precise, even when facing the stress shielding of dense outer layers, if we use proper force transfer medium that is matching to the internal layers we target. So these things together, they make the ABR technique. So in that sense, right now you can see that things are very straightforward. So ABR technique and the 3Q methodology could be summarized in a very straightforward way. So key conclusion, compression without distortion has enormous potential, but it is counterintuitive. Although it's counterintuitive, it is very much possible. And not only it's possible, but it has tons of benefits to it. It provides many times greater internal impact than intuitive compression with deformation, or with major deformation, namely distortion, right? And it provides the ability to target the weak internal layers, the core essence of the imbalance, right? Bypassing the stress shielding effect and like going through this dense outer shell without distorting it. So the other aspect that I want to highlight is that compression without distortion is possible, but it is very special. It exists only in a very specific range, right? In my earlier presentations, I talked about 1 to 2% deformation if you want to have this numeric level to it. And to benefit from compression without distortion, the technique has to be done by smart design and not by a fluke accident. And to complete this message, right, I hope that this video has helped you in getting a clear idea of the ABR goals and ABR technique essence. But more importantly, it connected you to the bigger ideas. That's the key. And the key is straightforward. What is the most important process that we are facing when working physically with humans, especially with kids affected by cerebral palsy, the ones who have profound imbalance? The most important thing is mechanotransduction. Mechanotransduction, mechanical feeding, to say so, right? It's the fundamental process that converts your external mechanical work into remodeling of tissues, and namely gives the basis of transformations, gives you the working instrument. But as an instrument, it's kind of double-edged. Mechanotransduction can be your friend or it can be your foe. And that's essential to understand. So if you do your external mechanical work smartly, if you deliver it smartly, respecting the ways that the responses are arranged within the body, and if you're really looking for the proper uniform response and actively, specifically looking at how to correct the imbalances via the uniform loading, so then mechanotransduction is your best and most important friend and ally, providing you with the ability to remodel and build weakened and depleted fascia tissues in your child's body. But the opposite is true as well. If your external mechanical work is done blindly, without knowing what mechanical impacts you deliver and how, if you work on illiterate basis, and if you are misguiding yourself by following I am rewiring the brain line of reasoning, well, then mechanotransduction becomes your foe and nemesis, punishing your flawed thinking by aggravating the imbalances in your child's body. I mean, sad but true, that's the fact. It's either your friend or it's your foe. And the fact is, you can't run away from mechanotransduction. Every mechanical interaction that your child has with external surroundings, whether it's sitting, standing, crawling, pushing, wheelchair, anything, result in mechanotransduction effects. And you don't have a choice of avoiding mechanotransduction or pretending it doesn't apply in your case by hiding behind all this crap, signals and training and patterns and reflexes. Well, these are the electric aspects that exist, but it's apples and oranges. We talk about apples, right? If you want a better apple, you have to do something that improves apples. Don't hide behind oranges. So your only choice is becoming smart and making the mechanotransduction into your most powerful friend, or otherwise you have to face the music. If you decide to stay ignorant, to stay illiterate, well, then you're paying the price of having mechanotransduction as your worst enemy, because it's the enemy that you can't sort of see, right? It's like the proverbial thing with the frog. If you heat up the water at once, the frog jumps out. But if you raise the temperature by 1 degree to 10-15 minutes, then the frog gets boiled alive. That's the same thing. It's But the mechanotransduction effects and the mechanotransduction effects on the imbalance, they're like a compound interest, but it's like a credit card debt interest, which works against you. So you either invest and then the interest, the compounding interest starts working for you, or your debts, they accumulate, developmental debts, to say so, into dramatic imbalances in your child's body. So whether it was enlightening or not, and I don't want to finish on this pessimistic note, but my goal is to make things clear. So to leave no ambiguity and to make sure that you understand where we're coming from, what are the realities that you face, and then from that place you can take educated choices and make intelligent decisions. So thank you very much for your attention, and I hope it has been educational and beneficial.